You're on the 80th floor of a glass tower in the middle of a city. The wind is hammering against the windows. You're trying to focus on your laptop, but you can feel something. A faint, almost imperceptible movement in the floor, like being on a very large boat in very calm water. You glance at the lamp on the desk. The chain holding the shade is swaying. Just a little, just enough to make you wonder, is the building moving? How much? And how is it possible that 100,000 tons of steel and concrete bolted to the ground are gently rocking back and forth like a tree branch and nobody seems concerned? Here's the question nobody really stops to ask. Why don't skyscrapers just fall over? What's actually keeping a 2,700-foot tower upright in a 100-mile-per-hour wind? And how is it that the engineers who designed it wanted it to sway on purpose and got into serious trouble exactly once when one of them realized he had miscalculated by 40%? The answer involves a 450-million-year-old rock, a Princeton engineering student writing a term paper, and a 660-ton steel ball hanging by 8 cables in the middle of one of the world's tallest buildings. Here's the first thing most people get wrong. They think a tall building has to be rigid, stiff, locked in place like a steel pole driven into the ground. That feels intuitive. It just happens to be exactly backwards. A skyscraper that doesn't move is a skyscraper that breaks. The taller the building, the more it has to bend. The Burj Khalifa in Dubai, currently the tallest building on Earth at 2,717 feet, is engineered to sway up to about 1.5 meters at the top, roughly 5 feet in heavy wind. Taipei 101 in Taiwan can drift 60 centimeters in either direction in just 5 seconds during a typhoon. The Empire State Building, built in 1931, has been rocking gently in storms for nearly a century without a single structural failure. S isn't a flaw the engineers tolerate. It's a feature they design into the building from day one. The standard rule among structural engineers is that a tall building can sway up to 1/500 of its total height before occupants start feeling motion sick. So a 1,000-foot building is allowed to drift up to 2 feet at the top in a strong storm. That's not a rounding error. That's geometry doing its job. Why must the building bend? Because at 1,000 feet, the wind isn't a gentle breeze. It's a constant force pressing against thousands of square feet of glass and steel. If the building were completely rigid, that force would have nowhere to go. It would build up inside the structure, twisting joints, snapping welds, cracking concrete. By letting the building flex slightly, engineers convert that force into harmless motion. The skyscraper absorbs the wind the same way a skyscraper tall tree does, by bending. Quick favor before we get to the part that should genuinely surprise you. If you've ever wondered about the engineering hiding in the buildings around you, hit that subscribe button. We dig into the science behind the structures you walk past without thinking. Now back to the swaying. The first time anyone built a tall building this way was in 1885 in Chicago. After the Great Chicago Fire of 1871 destroyed most of downtown, the city rebuilt with a hunger for height. An engineer named William LeBaron Jenney designed a 10-story building called the Home Insurance Building. Until that point, every tall structure in history had supported its own weight through thick masonry walls. The taller you went, the thicker the walls had to be at the bottom. Eventually, the walls would be so thick, there'd be no room for windows or rooms. The Home Insurance Building did something completely different. It used a steel skeleton inside, with thin masonry walls hanging off the frame like curtains. The building weighed only 1/3 of what a traditional masonry building of that height would have weighed. Chicago officials were so worried it would topple that they halted construction to investigate. It didn't topple. It stood for 46 years until it was demolished in 1931, and every skyscraper built since has used a version of the same idea. A steel or concrete skeleton on the inside, doing all the structural work. The walls are just there to keep the weather out. But the skeleton needs something solid to stand on. This is where the foundation comes in, and where most people miss something important. Underneath Manhattan is a layer of metamorphic rock called Manhattan schist. It's about 450 million years old. It's so strong it can support 10 to 40 tons per square foot of pressure without failing. In Times Square, that bedrock sits about 18 feet below the street. In other parts of Manhattan, it can be 260 feet down. To build a skyscraper, engineers drill or excavate through soil, sand, and water until they hit the schist, then anchor steel or concrete piers directly into the rock. The building isn't sitting on the dirt, it's clamped to the planet itself. For decades, urban legend held that this is why Manhattan has so many skyscrapers, because the bedrock was conveniently close to the surface. More recent research has actually challenged that idea. Some of the city's tallest historic buildings, including the Woolworth Building, were actually built over some of the deepest bedrock in Lower Manhattan. The real driver was economics, not geology. Where the rents were highest, developers paid for whatever foundation engineering was necessary. The bedrock wasn't a free gift, it was a bill they were willing to pay. Now here's the part that should genuinely surprise you. Even with a perfect foundation and a flexible steel frame, very tall buildings have a problem the shorter ones don't. They want to sway and sink with the wind. Wind doesn't blow steady, it comes in gusts, eddies, and rhythmic pulses. If those pulses happen to match the building's natural swaying frequency, something dangerous starts to happen. The building keeps adding energy to its own motion, swaying more and more with each gust. This is called resonance. It's the same phenomenon that lets a child on a swing go higher and higher just by kicking at the right moment. For a tower 100 stories tall, resonance is genuinely dangerous. It can make a building sway so violently that occupants get seasick, glass cracks, and structural elements fatigue. The solution sits hidden in the upper floors of nearly every super tall building constructed in the last 50 years. It's called a tuned mass damper. The most famous one is in Taipei 101 in Taiwan. Suspended between the 87th and 92nd floors of the tower hangs a steel ball 18 feet across, weighing 660 metric tons. It dangles from 8 enormous steel cables and is connected to 8 viscous shock absorbers. When wind pushes the building one way, the ball lags behind, then swings the opposite way, pulling the building back toward the center. It reduces the building's sway by 30 to 40%. During Typhoon Soudelor in 2015, when 100-mile-per-hour gusts hit Taipei, the ball swung a full meter inside the building. The damper is so impressive that Taipei 101 made it visible to the public. You can pay $16 to walk around it on the observation deck. Tuned mass dampers exist in dozens of skyscrapers worldwide. The Comcast Center in Philadelphia uses a 1,300-ton water-filled column that sloshes back and forth. 111 West 57th Street in New York City contains an 800-ton solid block damper. Almost every tall building in earthquake zones uses one. They don't make the building safer in the structural sense. They make it more comfortable. They prevent occupants from feeling like they're trapped in a giant slow-motion metronome. But not every skyscraper got the math right the first time. In 1977, a 59-story tower called Citicorp Center opened in Manhattan. It was structurally radical. To accommodate a small church on the corner of the block, the structural engineer William Le Mesurier placed the building's 4 massive support columns at the middle of each face rather than at the corners. The building was held up by a system of diagonal steel braces. It was the very first skyscraper to install a tuned mass damper. In June 1978, a Princeton engineering student named Diane Hartley was writing her senior thesis on the Citicorp Tower. She calculated the stresses on the building under quartering winds hitting the corner at 45 degrees rather than straight on. Her numbers came out higher than what Le Mesurier's firm had told her to expect. She raised the question with a junior engineer at the firm. The question made its way back to Le Mesurier himself. Le Mesurier ran the calculations. He found that quartering winds increased the load on certain braces by 40%. Worse, he discovered that during construction, the welded joints he had specified had been quietly substituted with bolted joints to save money. The welded design could handle quartering winds, the bolted design could not. A 70-mile-per-hour wind, which hits New York roughly once every 16 years, could collapse the building. Through August and September of 1978, welders worked at night, secretly reinforcing 200 joints with steel plates, while a New York newspaper strike kept the story out of the press. Hurricane Ella was approaching the East Coast during the repairs. Evacuation plans were drawn up for 200 city blocks. The hurricane veered out to sea before it hit. The repairs finished in October. Citicorp Center has stood ever since. The story didn't become public until a New Yorker article in 1995, 17 years later. Here's the part that should genuinely surprise you. You've been living surrounded by versions of this same engineering your whole life without realizing it. Every tall vertical structure designed to face wind uses some version of the same playbook. Flexibility plus resistance. Anchored base plus damped top. Radio and television broadcast towers. They flex visibly in strong wind by design. Wind turbines. Those 300-foot blades on a 400-foot mast bend in gusts. They have to. Suspension bridges. Engineers learned this lesson the hard way when the Tacoma Narrows Bridge in Washington oscillated itself apart in 1940 during a moderate wind. Modern suspension bridges incorporate dampers and aerodynamic deck designs to prevent resonance. Offshore oil platforms. They're floating skyscrapers anchored to the sea floor. Same flex and resist principles, but with waves instead of wind. Power transmission towers in storm zones. Designed to flex. The pedestrian Millennium Bridge in London famously had to retrofit dampers in 2000 because it swayed alarmingly under foot traffic. Even your average tall ship's mast. Same principle. Bend, don't break. Every single one is doing the same fundamental thing your skyscraper does, letting the wind win a small battle in order to win the war. Now for the honest trade-off. Skyscrapers aren't immortal. They sway, which means upper floors can feel motion that some people genuinely can't tolerate. Hotels in tall buildings sometimes hand out notes warning guests that the building may creak in high wind. The Grand Hyatt in San Francisco does exactly this. Tuned mass dampers cost millions of dollars and require ongoing maintenance, sensors, and backup power. Earthquake zones add an entirely separate layer of engineering, with isolation bearings and base isolation systems that allow the foundation itself to move slightly while the building above stays relatively still. And every building has a design lifespan. The original home insurance building lasted 46 years. Most modern skyscrapers are designed for 60 to 100 years of service before major retrofitting. So here's where you land. That faint motion you felt at the 80th floor wasn't a flaw. It was the building doing exactly what its engineers spent thousands of hours making sure it could do. Bend without breaking. Sway without falling. Convert wind into harmless motion that you can almost but not quite ignore. You've been standing on top of a steel skeleton anchored to 450-million-year-old rock, rocking gently inside the limit of 1/500th of its own height, balanced by a giant ball of steel hanging in the ceiling somewhere above you. That's not luck. That's 140 years of engineering, one nearly catastrophic mistake quietly fixed in the dark, and 3 independent systems all doing their job while you wait for the wind to die down. If you think tall buildings are weirder than they look, wait until we get into why some modern skyscrapers have actual holes in them. Big openings cut straight through the structure near the top. Because the reason isn't to save weight or to look cool, it's to outsmart a force called vortex shedding, the same invisible phenomenon that took down the Tacoma Narrows Bridge in 1940, and that engineers have been quietly designing around ever since.